improved significantly by Baldi and Morin to only 1 over r to the power c divided by n. So this is a big step by removing the exponential logarithm in this one. So one of the fundamental things that the hierarchies of lower bounds are built on are the positive statistics. This positive statistics is just saying we can rewrite polynomial such that it is super clear that it is non-negative. And roughly speaking, very roughly, you can write it in this form. It's a polynomial is equal to something that is globally non-negative and terms that are positive on the set that you want it to be positive on. So typically the constraints that generate the semi-algebraic set. But we want to look at where these sigmas are not equal to the sum of squares situations. So then there is the question, what kind of forms of a positive statistics can we use? And probably also useful in practice, what is the rate of convergence that we can get with them? So the basis for the hierarchies of lower bounds for the Lasser hierarchy is Putinas positive statistics. This is the same form as the normal Lasser hierarchy of lower bounds, but without any degree restrictions. And naturally, to have convergence, you need that the quadratic module generated by this is Archimedean. To avoid going into Archimedean too much, we replaced the Archimedean property by adding an artificial pole large enough around it, since this function can be generated by the g's if it's Archimedean as well. So we don't have to look at the Archimedean property, and this is a very nice thing to have for other classes. Since you only need n plus 2 SOS polynomials. So let's see, can we do something with other classes? And when I talk about other classes of SOS, then SOS polynomials, first thing that everybody should say is, oh, Motzkin. This is something that is really non-negative polynomial. That is not an SOS polynomial. You can generate it by looking at the arithmetic mean geometric mean inequality, which is this inequality. And we're going to replace the xi's by these three things. X to the power 4 times y squared, y to the power 4 times x squared, and 1. So when writing this out is this inequality x squared y squared less equal than that expression. And multiplying both sides by 3, you get the Motzkin polynomial if you move them all to one side. So this is a polynomial that's not SOS, but there are luckily other classes that do capture this kind of polynomial, namely the sum of non-negative circle polynomials. So it would be nice if we could have a nice hierarchy of lower bounds for that. So look at what are some of the obvious choices as alternatives. Like I said, the sum is there. It can be represented using relative entropy programming or even the second order cone problem. There's slight asterisks on it because second order cone is quite huge to do that. But you can also go for smaller classes of polynomial, which is especially useful for large optimization problems, such as SDSOS, which is a second order cone problem, and DSOS is just an LP. So this is relevant because even though SDPs are super great, they do have a scalability issue, which can possibly be solved by using something computational cheaper, like a second order cone. So let's see, can we get something hopeful and see that we place the SOS by another class and be fine? And the answer is quite obviously no, otherwise we would already be very happy. So there are all the classes that I currently mentioned, this does not work for. And there are 3 good counterexamples that show this, that it's really fundamental that this does not exactly work. And we're going to look at the example from JOS. And this is a very nice example because it is very small and a very simple semi-arithmetic set, namely 2 variables on the unit ball and a quadratic objective. And with using the non-SOS polynomials, we don't get anywhere near. The best lower bound that you can get for it is -2, but it is already clearly a non-negative polynomial. So besides that this implies that the naive Poutine doesn't work, this also implies that the naive Smootchen result for SDOF does not work. So we have to find something different for this class polynomial that may work. And here come our results in, and this is the K-Poutine. The K-Poutine, where the K stands for the class of polynomials that you use, have the standard properties so that you want it to be inside large enough ball, the semi-algebraic set. And we have that the polynomials are in the form from something positive over the ball, plus something that gets helps with solving the constraints. So let's look a bit in this the variables that these polynomials are into. These can be considered in the lower bounds, upper bounds, and the ball constraints. So this is a sort of way to enforce sort of Archimedean property, even though you don't need it. Okay. So, like I already said, these are the types of polynomials that could possibly be very interesting because they are computationally cheaper. And we only need one assumption for the class of polynomials that we look at, and they should just contain the monomial squares. So all the classes we so far mentioned clearly satisfy it. If there are any questions in the meanwhile, please interrupt. Then we're going now into the convergence rates, at least a very quick overview about some of the steps that we use. So for the Poutine convergence rate, what we first want to get is a Smootchen type convergence rate over the unit ball. Because with the unit ball, it's a very simple set that we can work with and transform it into a Poutine type form. And then when we have that result, we extend that result to any semi-algebraic set. Okay. So here is the Smootchen type result that we're going to use. And that's by Curianikova, Pompera, and Luis Vilaga. And that's, again, is evaluated in the lower bounds, the upper bounds, and the constraints, all to very high power possibly. But I will show that that is hopefully not the case. And we're going to apply this for the only constraint that we have, being the unit ball. So the G is only this term. And we can show that we have a level of hierarchy R equal to its order of the norm divided by the minimum of 2 to the power 3. So the error rate is 1 over the left of the hierarchy to the power 1/3. So that is at least a good result for the ball. And let's give a short overview of how we get there. I will be skipping quite a few steps. And the way that we're going to use it is that we're going to go from non-negativity of the ball to non-negativity of the positive orthant with some ball constraints, and we get it to the simplex in which we can use polia. So that is the way that we rewrite this polynomial P in the form of a different polynomial that is positive on the set that we want to look at. The first step that we do, we originally had a ball centered around 0, and we're going to shift that ball with all the influences up to the positive orthant. So we move to the overbounds. Then this ball is contained in a large enough simplex, which we then can use. So we now call the set P1 bar the set of the simplex with the ball constraint, and we want to make it the equality for a nice trick that we're going to use. So that is why we use an extra select variable y. Okay. So this is the trick that we want to use. This is a result by Peña, Pera, and Zulaga. And that says that if you have a polynomial that is positive on a compact set with an equality constraint, then there's constant that you can multiply with that constraint squared, so that you can extend it to non-negativity over the entire set that you were looking for. So this way we want to get rid of this equality and just get the simplex result that we can work with, because we have the great result from polia. Are there any questions about this part? This is a very fast overview about something. So let's get into polia. Polia is actually defined for homogeneous polynomials, and says that you can put multiply it with e transpose x to some power r, such that this product only has positive coefficients. So then you know it is non-negative on the positive orthants. So then you would be happy. And Paus and Resnick already showed very early on that the boundary that you have is of this type. So this is linear in the norm divided by the minimum. And we can actually extend it to the non-homogeneous form, and we want to get rid of just the unit simplex and go for the simplex of range n. So this is then a result that Gerard all at least showed. I don't know if there are earlier results that already also showed this issue. And this the trick to get this result is that we start out with polynomial for which we know it is positive on the simplex with radius m. We homogenize it, but we don't use the standard homogenization, but we use it that we add homogenization with respect to the simplex term. And then by expanding the homogeneous polynomial, we can separate it into this form using
LP above and LP below the same.
Yes, that LP is just the largest coefficient without the binomial multinomial term.
In the mononomial.
So the main thing that changes is this m to the power d takes care of the size of the simplex. And yeah, that's the main step, and the homogenization step. That's this term that speaks for itself. Then.
Well, if you put the binomial coefficient in the presentation, you may remove this.
Yeah, there is a way. This was also what I quickly mentioned. If you would instead go for the Handelman form, there are some tricks that can be done there to almost that much question. So,
Yeah, okay.
can you please re-ask?
So I was saying if you put the binomial coefficient in the presentation and take the same the max norm of the coefficient,
Yeah.
then you have the same inequality as Fourier. Above.
Yeah.
No factor m.
Yes, but we want to explicitly use this m here because we have.
You have it for the delta m.
Yes.
Okay.
So this p min, this is the minimum that we use. So this minimum is different than this minimum. This is minimum of the simplex with equalities of size 1, and this is inequalities of size n. So when we combine the previous steps, we had that new polynomial that we generated that was positive on the large simplex that we used, which is called f, which we created that its minimum is still very close to the odd minimum that we used. And the largest coefficients in that binomial form is only in the form of the to the power 2 to the power 3 times the original form. Then using the previous results by filling it in with this new polynomial f, we get our convergence rate is this LP divided by p min to the power 3. With some coefficients in front of it that do not influence convergence rate at all. Okay. Level. And we're going to use this result to get the Putinaar certificate on this unit ball. And and the way that we do it is again, we're going to take. Let me quickly go back to the smooch. I've not mentioned this m here. This m is arbitrary low and upper bounds that you can choose as long as they are large enough. And we are specifically going to use it for the Putinaar result with this m being n plus 1 divided by 2, such that we can eliminate all of the odd terms. Because each of the odd terms can be written in the form of 1 plus minus xi and the ball constraints. So this is without any change of the degree except for just doubling the degree, but doubling the degree does not change the convergence rate. So for the unit ball, this k Putinaar result is also of the order 1 over r to the power 1/3. And this is the part that sort of the painful step for the Putinaar, k Putinaar result comes. The nice thing is that we only need univariate polynomials to handle those constraints, but these constraints that we're going these terms that we're going to add could be very high norm and high degree. So for SOS polynomials, you could typically solve this then like Lorenzo did with the kernel and univariate approximation that fits as nicely as possible, such that the norm does not explode. That luck we don't have in the univariate case and for non-SOS. So there is definitely some improvement possible if you go for multivariate approximations using, by example, SONG. But we have not found it yet. So that is hopefully a nice part that can be added at some point. So we are quite limited in the options that we use. So the solution that we are going to get is that we make this polynomial that s equal to something very small, because of course this is already no set that you are positive on. You don't want to get outside the too low there, that you go negative inside it. And if you are outside, polynomial that you can look at is possibly very negative, so we have to compensate for that. So we want that if you have this interval to be the ball, you want the polynomial to be very high to compensate for very negative be outside of S. So the degree that we get here is also how the LP divided by P min to the power the lowest P exponent, which if you have what's called quadratic constraint qualification conditions, then this lowest exponent is equal to 1, as shown by Lorenz M again. So in this form, that you want the function that you get multiplied by the constraint be below the original polynomial, that if you subtract it, then the remaining polynomial is non-negative on the entire ball you look at. Exponents. This is comparable to the results previously known for the SOS, which was by Lee and Strykover from 2006, I believe. So hopefully in a few years there can be an improvement in this part as well. So again, if we just showed the upper the degree bounds that we got, and from the degree bounds you can go to the convergence rates, and convergence rates is then 1 over ln r to the power c being constant in terms of energy, and if you have constraint qualification conditions, it is ln r divided by ln r. Can I ask what time it is?
So almost 4:30.
28.
Okay.
4:28.
So this as a relaxing throwback. In the beginning, I showed you the very painful result that just illustrated that you cannot get real Putana or real smooching with the SOS polynomials, and we can show that at least very illustratively this is an SOS polynomial and things of use. So it is very easy to see positives that it can be written non-negatively, but even already at degree 2 you get something that is approximately optimal value with our hierarchy with the SOS. So one of the parts that makes SOS useful for large scale optimization, and that is the sparse structure that it can exploit, typically using the running intersection property, and there are some other term sparsity being exploited. So we already mentioned that there's univariate polynomials considering for the constraints. So we preferably want to get some sparse expressions that we can do for our reduction to the ball. The ball itself is a very dense large problem that we can get. So here we're going to use the correlative sparsity. And the idea is we want to split the large ball into smaller balls, each of them having smaller issues. And this is, I will just do it intuitively. So suppose you have a polynomial in 3 variables that you can be split in polynomial in 2 variables, x and y and z. Then it's clearly that if you have both p1 and p2 being non-negative, then the original p must be non-negative. But the other way is clearly not true. You can have non-negative p, and then one of p1 or p2 is negative at some points. But for that, we can use some tricks to not really look at p1 and p2, but be adjusting a bit. So we're first going to look at our running intersection property, that we want to split the original ball into smaller balls that each corresponds to a section of the running intersection property. So in this case, x and y club and y and z club. Then we can adjust p1 and p2 by adding the minimum of the other one to one and subtracting it from the other to get p1 tilde and p2 tilde that are positive on their respective cones. And then you only have can add the Futina results up for each of those smaller polynomials. So this again requires the running intersection property that can be explained using the causal structure of the representative graph. Okay. So this is then just displays how those big problems can be then split into the small problems into one hierarchy. So we end up at our summary and conclusions. We want the goal of this idea was to make alternative types of polynomials useful and more accessible to use in research, especially when you have cases that the SVPs for sum of squared polynomials do not scale well. There are the convergence weights that I've shown that for the specific cases are very good, but for the general case for Putana, the K-Putana version can probably be improved significantly. So thank you for we are currently using it for AC optimal power flow, and we got already some results better than currently there are. So it's actually kind of useful. Thank you for your attention.
So for SONC, there is a Putina theorem.
I don't think so.
Well,
For SONC, there is Marijke Drijsselen that has a positive self-start, but
yes,
this one is stronger.
Yeah, presentation.
Yeah, this one can be used to imply Marijke's.
So This will be applied.
This literally implies a result. So you can, for a specific class of polynomials, this is a framework that you can use to work with it such that it works for your specific problem. I assume that you meant Marijke Dessler's positive sensors, right?
Yes.
Yeah. This was a good inspiration also when I read it.
So is it? Did you try this in practice?
Yes.
So how do you have some comparison?
I don't have numerical comparison already, but we use it for the AC optimal power flow, that's it. And there, because you have the sparse structure, you can combine both the Bunning intersection property to get very small result problems. I mean, very small sets of variables for the Bunning intersection property for the buffering. And then with the SD source for the bulk constraints and using SOS polynomials for the univariates, we got some new results.
And with say the classical SOS, maybe not the non-sparse case.
I think that at the moment, if because it's a polynomial in 2n+1 variables, that you do need some sparsity to effectively.
I mean, the comparison when you want to compare the approach where you choose the specific codes or this specific representation and say some SOS representation. So it would be good to compare on maybe small examples, classical examples.
Yeah, we got some small examples throughout the paper, but that is then on the side that both of them solve it quite fast. And I think for the ones with the non-sparse, both of them struggle. I have not done too much numerical analysis yet. We just took this specific problem. Thank you for the question.
Yeah.
Do you have any idea whether the convergence that you get is optimal for the smallest problem to consider?
Oh no, we did for some of monomial squares because that's the smallest thing. So if you do it for SD source or SONG, there are probably better ways available.
But for some monomial squares, explicitly conventional, we know this convergence that is sharp.
I cannot say. I think it is close to sharp because it's like there is both of them are linear problems and just the who's now a Handelman transformation that is the only difference that can make those are sharp. So I think I can at least for some examples created that it is sharp. But that is really the worst case. In practice, things often are not in the worst case, I hope.
Other question? If not, we thank you.